When dealing with wave phenomena in general, uh, one of the most common things that you have to do is superimpose multiple waves together to find a resultant wave. And there are several techniques for doing this, but in essence, the ones that are most important for us will be adding waves from two different sources, or maybe more than two sources. I'll look at it in the picture of just two. But what you have to deal with the most, not 100% of the time, but probably 95% of the time, you're going to be trying to find the resultant field at a given point P that result from two different sources of waves, S1 and S2 here, or more than that. But uh, the waves will have exactly the same frequency. They're propagating in a media that has a nice uniform media, so I'll think of it as a vacuum here, but it could be any media that has a constant uniform speed of the wave. And they have the same frequency, so they have the same wavelength if the C is the same in all directions and for all values. And but the only difference is I'm going to have two waves at different points. The source of them, S1 and S2, source 1 and source 2, are uh, uh, are probably point sources or something approximating point sources. But at least for our purposes here, I'm going to be looking far enough away. R1 is far enough away so that by the time they get to the observer or the detector at P, uh, that it's a plane wave, and likewise from S2. R2 is far enough away, even though it might be a point source, but by the time by the time it arrives at this point P, uh, then it's effectively a plane wave. And so at the point P, uh, well, we could we could delineate the wave from source one. I'm thinking of as an electric field, since we're dealing with optics, but it could be the height of a water wave, or it could be an acoustic wave. Doesn't really matter. In the plane wave approximation is going to be A1, the amplitude of this wave from the source, sine k times r plus or minus omega t. A lot of times people will use x along this distance, so this would be x in general. And likewise here from S2, it is electromagnetic wave, and so I'll just look at the single amplitude E2, which is the dominant port, and then A2 is its amplitude, and I'll look at it as being sinusoidal as well. Could be plus or minus here, depending on the direction these waves are moving. Particularly if it's all in one dimension, this could all be in the x, and one could be going to the right, and you would have minus. One could be going left, and you would have plus. But I won't worry too much about those two things at this juncture. At P, I've got some sort of detector. It might be, if these were sound waves, might be my ear. For light waves, it might be a photoresistor or something to detect the incident light that is on there. But what I know is that by the time I'm at point P, that I have to superimpose these two waves, and they will just simply add together. But we have to be careful how we do that. So writing these down below, we have this expression, and then there's some auxiliary terms uh, that is useful to introduce. Uh, One is just the k times r1, and I call that alpha 1. It's really just this constant phase the source isn't moving or anything, and so once I've got this distance and I know the wavelength of it, then KR1 is just going to be some number. And likewise from 2, KR2 will be some number which I call alpha 2. Now I'm looking at waves that are in phase, and ordinarily you could have an additional phase shift on this one and a phase shift on this one, but I'm assuming at the sources that they're in phase. Mm-hmm. So it's easy to handle the phase shift. You just have a plus phi1 here and a plus phi2 here, but ultimately we will lump all those together into alpha 1 and alpha 2. Delta is the difference in those phase factors. So I generally define it delta as alpha 2 minus alpha 1. And if you look at that and plug in what all these things are, this simply is K times delta R. Oftentimes people use X for these, so don't be surprised if you have an X term here, and they'll see 2 pi lambda over delta X. And that's the phase difference between the two sources, the source from source 2 minus source 1, so this is the difference in the phases of these two waves up here. Right? Now I'd like to write this, like to write E as sort of the fundamental problem here in the form, the total field in the form of some amplitude to be determined times the sine of some phase for it to be determined, and then plus or minus omega t if it's traveling in at some point. So I want this to be true, this equation up here, that by the time I add these two waves together, I get something that looks like this. I'm assuming I know the frequencies, I know whether they're going to the right or to the left. So really it's a matter of determining A and determining this angle theta for the combined superposition of E1 and E2. One can write these in what is sometimes called a phasor diagram, and in which usually you look at them at t equal to 0. So this t equals 0, these terms go out, and then I can plot the amplitude of A2, that's here, and the angle that it makes with the origin, with the x-axis on this particular diagram here. Likewise for A1, it's of this length, and it has this angle alpha 1 once I've set t equal to 0 on it. And then I want to sum those together to add E1 and E2 to get a resultant. And you can view these really like vectors in this vector plane. And as vectors, I know that I can use the parallelogram rule to add these two vectors. I simply complete the parallelogram and draw the diagonal, and that's going to be the new vector E, which is A, and its angle associated to it is theta. Well, if you look at these, that was at t equal to 0, but now then if I add in omega t, well then each one of these will begin to increase, the total phase will begin to increase, and so this whole, really will rotate as a rigid body in a certain sense, and it will rotate either in the positive direction if it's positive, or in the negative direction if it's negative. But the overall orientation of these won't change, the relative position of it. Now one way you could write this is to translate this vector down to this end, which I've done here. So I've got A1, A2, E2. So E1 to E2, and then the resultant is this. And that's just translating this vector over to this side in this vector diagram up here. Sometimes that's a little bit easier. Alpha 1 is this angle with the x-axis. Theta is the angle of the resultant with the x-axis. And if you look at the alpha 2, it is the total angle alpha 2 is with the x-axis, and so alpha 2 is really all of this here, alpha 2. It's this whole angle is alpha 2. But if I take the difference, alpha 2 minus alpha 1, that's just delta. So the angle, the difference in the phase, and that's the difference of phases, is alpha 2 minus alpha 1, and that's just this from the direction that E1 is to the direction of E2 is just the difference in those, so that angle is anyway. And that's what we want. And one way that you can get it is the following. If you look at this triangle EFG, so triangle E right here, F is this point, and G up here, I've got a triangle, and I can use the law of cosines on it. So if you remember the law of cosines, I'll look at this angle here that's not marked, and I'll take the side opposite this angle is a squared, and that's got to be the sum of the squares of the two legs. One is, this side is A1, this side is A2, minus 2 times A1, A2, times the cosine of this angle. And if you look at that angle, you'll see that this angle is delta. That's alpha 2 minus alpha 1. Then this angle is 180 minus delta. So this becomes cosine of 180 minus alpha, minus delta. And I'm assuming now that we have all of those things, so I'm given alpha 1, alpha 2, or I know those, A1 and A2. And so one can just enter this formula. The cosine of 180 minus delta is minus cosine delta, and so the minus makes this a plus. And so the amplitude of the resultant wave, which is usually one of the things that is of most interest, is just the square root using the law of cosines of that quantity there. To get the angle, well, you can kind of treat these as vectors. You get the x and the y components of this vector E1, and the x and the y components of E2. And the total for E is that it will have EX, and its resultant is this vector here, so it's going to have EX and EY. That's just the sum of the corresponding components of E1x, E2x, but those are just A1 cosine alpha 1 plus A2 cosine alpha 2. And then E1y plus E2y, and that's just the amplitude A1 sine alpha 1 plus A2 sine alpha 2. And again, we know we've been given, or we know for any given waves, their amplitude and their these phase factors, alpha 1 and alpha 2. And so we can get EX and EY, and that's really just the components of this big E vector. It's X component, and then projecting over here, it's Y component. And to get that angle theta, that's just the Y component over the X component. So it's this term over this one, where I could have substituted these in. But so this is, I generally view this as sort of a vector method, treating them like vectors, these wave directions and the waves. And I calculate, from the givens, I can calculate the amplitude and then the tangent of the angle in this fashion. Method 2 is similar, that is actually the way that I probably would do it most of the time. This one works best if you've got a whole bunch of fields and I want to sum all of these up to get an overall resultant. And what you do is just do that vector xy decomposition for each one of these vectors, sum up all their x components, sum up all their y components, and get what I call Sx and Sy. The amplitude of the resultant vector, that's the sum of all of those, is just the square root of Sx squared plus Sy squared, these quantities up here. And then finally, the tangent again, well, once I've got the x and y components, I can compute the tangent as just its y component over its x component. And then you've got the electric field, the sum of n different n-phase waves, all having different amplitudes, different distances away, perhaps. I can sum all those up and then put them in the form A sine theta plus or minus omega t, using this value for A, and then the angle theta that comes out of this for theta.